Welcome to Study Loop.
Happens in burning. We can choose a normal carbon-based compound burning in oxygen to produce carbon dioxide, but let's take a better, more interesting example of burning: water. Not water burning, but water as a product of burning. When hydrogen burns in the presence of oxygen, it becomes water. So effectively, water is the product of burning. It's the equivalent of ash that forms It's the equivalent of ash that forms when some carbon compound is burned, but instead when the hydrogen compound is burned. This is why water is an extinguisher, because it's basically ash and it can't burn anymore. When you douse your flames with water, it has to die out because of the lack of oxygen. But regardless, now, how is this similar to nuclear fusion? It's because a hydrogen atom has some binding energy, and an oxygen atom has some binding energy. But let's say the energy of hydrogen atom is minus E1. It's negative because the initial hydrogen molecules became the initial hydrogen atoms became hydrogen molecules, which means hydrogen molecules are initially stable. That is why the binding energy is always negative. So let's say hydrogen has a binding energy of E1 and oxygen has a binding energy of minus E2. The total binding energy here will be minus 2E1 minus E2. But when water forms, the binding energy, let's say, will be E3, and the total binding energy of the products here will be minus E3. Turns out this binding energy will be smaller than this binding energy. That is, if this was minus 8 electron volts, this would be minus 10 electron volts. So the magnitude of E3 would be larger, but because it is it is negative and larger, it will be smaller than the other side. This is how it works. This is very similar to how nuclear fusion works. Hydrogen atoms have a much higher energy per nucleus, let's say E1, and four of them become a helium atom. A helium atom. Let's say this has energy per nucleon of E2. Now, the total energy per nucleon on the left-hand side here will be 4E1, and the total energy per nucleon on the right-hand side will be E2, which means after the fusion reaction happens, because E2 is smaller than 4E1. 4E2. And this is energy per nucleon. So the total energy will be the energy per nucleon times the number of nucleons. So that's 4E2, which means 4E2 will be smaller than 4E1, and the difference is released as energy. Similarly, here too, this difference between the two reactions will be released as energy. But of course, there is one more similarity. It's that they need some activation energy. Hydrogen and oxygen don't start combustion automatically instantaneously. You need a spark that starts burning, and that energy will have to drive further burning. Similarly, even in fusion, hydrogen atoms don't automatically start combustion. You need a large amount of initial energy, which is why fusion bombs usually use fission bombs to initiate them. But there is one difference though. It is that the amount of energy released in nuclear reactions comes from the disappearance of mass and is very high. It's of the order of mega electron volts. Whereas in chemical reactions, it's of the order of electron volts, and it is solely due to energy